Module 1 Laplace Transforms. Contents 1.1 Definition of Laplace Transform. 1.2 Laplace Transform of Elementary Functions. 1.3 Properties of Laplace Transforms. 1.4 Laplace Transform of Periodic Function. 1.5 Unit Step Function or Heaviside function. 1.6 Inverse Laplace transforms. (1.61) Computation of the inverse of e power of minus as f bar of s. 1.62 Inverse transform by completing the square. 1.63 Inverse transform by the method of partial functions. 1.64 Inverse transform of logarithmic and inverse functions. 1.7 Convolution. 1.71 Convolution theorem. 1.8 Solution of linear differential equations using Laplace transforms. Initial value problems. These are the contents for Laplace transforms. Many physical problems, when analyzed, assumes the form of an ordinary differential equation subjected to a set of initial conditions or boundary conditions. Such problems are referred to as initial value problems and boundary value problems respectively. Laplace transforms serves as a very useful tool in solving these problems without actually finding the general solution of the differential equation by various known methods. The application of Laplace transforms is highly significant in engineering problems associated with electric circuits. 1.1 Definition of Laplace transform. If f of t means function of t, here t is independent variable and f is dependent variable. Function of t is dependent variable. T is independent variable. F of t is function of t is dependent variable. Is a real valued function defined for all t greater than or equal to 0, means positive integers. Then the Laplace transform of f of t denoted by L of f of t, means Laplace transform of f of t is defined by Laplace transform of f of t equal to integral of t equal to 0 to infinity e power of minus st f of t into dt, provided the integral exists. On integration of the indefinite integral. In the integral there are two types. One is definite integral and another one is indefinite integral. Indefinite integral anta heladre simple integral. Definite integral means limits are present. Upper and lower limits are present. Present irutte jotege ನಾವು ಅಪ್ಲೈ ಮಾಡಬೇಕು upper and lower limits na. We will be having a function of s and t. When this is evaluated between the limits t equal to 0 and t equal to infinity, we will be left with a function of s only, and we shall denote it by f bar of s, where s is a parameter, real or complex, means both real and imaginary value. So that is nothing but complex. Thus, Laplace transform of f of t equal to f bar of s. L f of t na f bar of s anta call ಮಾಡ್ತೇವೆ. Equivalently, we can express this in the form L inverse f bar of s equal to f of t. ಈ L ಇದೆಯಲ್ಲ, ಈ L ಅನ್ನು ರೈಟ್ ಸೈಡ್ ಶಿಫ್ಟ್ ಮಾಡಿದರೆ L inverse of f bar of s equal to f of t. L inverse of f bar of s equal to f of t and is called the inverse Laplace transform. Note: since linearity property holds good for an integral, we can obviously infer that Laplace transform of c1 f1 of t plus or minus c2 f2 of t equal to c1 into c1 take outside L into f1 of t plus or minus c2 take outside L f2 of t. Okay, this is linearity property where c1 and c2 are constants. Laplace transform of discontinuous functions from the basic definition. So, working procedure for problems. Step number 1. Here, f of t is composed of different functions in different sub-intervals of 0 to infinity. Suppose f of t equal to means when t vary from 0 to a, that time output of f of t is f1 of t. When t vary between a to b, that time output f of t equal to f2 of t. When t is greater than b, otherwise b to infinity, so that time f of t value is f3 of t. Then we consider the basic definition of Laplace transform of f of t. That is, Laplace transform of f of t equal to integral of 0 to infinity e power of minus st f of t into dt. Step 2. By taking into account the intervals involved in the given f of t, we express the integral in the equivalent form by using a property of definite integrals. Therefore, Laplace transform of f of t equal to first subinterval is 0 to a. So, e power of minus st f of t dt plus second interval is a to b, integral of a to b, e power of minus st f of t into dt. Third interval is b to infinity, e power of minus st f of t into dt. Next, step 3. We substitute the relevant f of t as in the data. Now, Laplace transform of f of t equal to integral of 0 to a e power of minus st. When first interval is 0 to a, that time f of t will be f1 of t dt plus in second interval is integral of a to b e power of minus st. That time f of t will be f2 of t and dt plus third interval is b to infinity. That time f of t will be f3 of t dt. Step number 4. We evaluate the integrals to obtain Laplace transform of f of t as a function of s. Note: if f of t is a polynomial in t, suppose this f of t is a polynomial in t, then we have to write integral of e power of minus st f of t dt as integral of f of t e power of minus st into dt. f of t ನಲ್ಲಿ polynomial in t ಇದೆ ಅಂತ ಹೇಳಿದ್ರೆ just interchange these places. First function it comes to the second function it goes to the first one. And use Bernoulli's generalized rule of integration by parts as follows. So now we are going to apply the Bernoulli's rule. Integral of uv dt equal to first function integral of the second function. First function as it is, integral of the second function, integral of v into dt minus ಫಸ್ಟ್ ಫಂಕ್ಷನಿಗೆ ಟೇಕ್ ದಿ ಫಸ್ಟ್ ಫಂಕ್ಷನ್ ಆ್ಯಸ್ ಡಿಫ್ರೆನ್ಷಿಯೇಷನ್. ಫಸ್ಟ್ ಫಂಕ್ಷನಿಗೆ ಡಿಫ್ರೆನ್ಷಿಯೇಷನ್ ಆಫ್ ದಿ ಫಸ್ಟ್ ಫಂಕ್ಷನ್ ಆ್ಯಂಡ್ ಅಗೇನ್ ಇಂಟರ್ವಲ್ ಆಫ್ ದಿ ಸೆಕೆಂಡ್ ಫಂಕ್ಷನ್, that is double integral. Okay, next first alternate sign, first time positive, next time negative, next time positive. So first function ಗೆ ಒಂದ್ಸಲ ಡಿಫ್ರೆನ್ಷಿಯೇಟ್ ಆಯ್ತಲ್ಲ, ಅಗೇನ್ ಒನ್ ಮೋರ್ ಡಿಫ್ರೆನ್ಷಿಯೇಷನ್, ಡಬಲ್ ಸೆಕೆಂಡ್ ಆರ್ಡರ್ ಡೆರಿವೇಟಿವ್. ಅಗೇನ್ ಸೆಕೆಂಡ್ ಫಂಕ್ಷನಿಗೆ ಡಿಫ್ರೆನ್ಷಿಯೇಟ್ ಮಾಡಿದ್ರಲ್ಲ ಫಸ್ಟ್ ಟೈಮು, ನೆಕ್ಸ್ಟ್ ಡಬಲ್ ಇಂಟಗ್ರೇಷನ್, ನೆಕ್ಸ್ಟ್ ಟ್ರಿಪಲ್ ಇಂಟಗ್ರೇಷನ್, ನೆಕ್ಸ್ಟ್ ಆಲ್ಟರ್ನೇಟ್ ಸೈನ್ ಆ್ಯಂಡ್ ಸೊ ಆನ್ ಅಪ್ ಟು ವೇರ್ ಫಸ್ಟ್ ಫಂಕ್ಷನ್ ಕಾನ್ಸ್ಟೆಂಟ್ ಆಗೋ ತನಕ ನೀವು ಈ ಥರ ಪ್ರೋಸೆಸ್ ಮಾಡಬೇಕು. ಗೊತ್ತಾಯ್ತಲ್ಲ? ಕಾನ್ಸ್ಟೆಂಟಿಗೆ ಡಿಫ್ರೆನ್ಷಿಯೇಟ್ ಮಾಡಿದ್ರೆ ಸೊ ದಟ್ ಈಸ್ ಝೀರೋ. ಝೀರೋ ಇಂಟು ಎನಿಥಿಂಗ್ ಈಸ್ ಝೀರೋ. ಓಕೆ.